This is the video podcast for Chapter 18 on the assessment of watershed functions using distributed hydrological models. In the previous video podcast, I went into some of the nuts and bolts about what does it mean to be distributed, and I didn't so much go into the hydrological flux part of that, and that's something that I'm going to do in this video podcast. In addition, I showed some examples in that were much more methodological examples, not so much hydrological and eco-hydrological results. So I'm going to change that now, and I am going to show you some of those kinds of results. And this is going to be another opportunity to look at our overall course theme on the impacts of human activities on the environment. Within that context, we've previously seen the use of paired basin studies to try to get logging impacts by looking at one basin and keeping it as a control, and then taking another similar basin, logging it, and seeing how the relationship between the two basins changes comparatively. With a model, we can do a similar idea. We can make one model of a basin in a natural state, and then we can do another model of it in a logged state. And through the intercomparison, then we can see what the effects would be. So we're not essentially using different watersheds in a paired basin context. We're using the same watershed in like a pre and post or different hypothetical scenarios. So to illustrate the kinds of things that a distributed hydrological model can do, I'm going to use some studies from a model called DHSVM, which stands for Distributed Hydrology Soil Vegetation Model. This is a model that was developed by faculty at the University of Washington, and its characteristics are given in this table on the left, and then a simple schematic of what some of the aspects are on the right, and I'll show those in the subsequent slides. In general, like all distributed hydrological models, it's going to solve a vertical energy and water balance for each individual pixel, and then it's going to be routing water down through the channel network. Well, not just channel network, but down the topography. So what kinds of model is this? It's a deterministic model. It's distributed. It's dynamic. That means it changes through time. It's at the scale of a whole watershed. The processes are at a single scale. It's designed more for scientific exploration than it is for management, although more and more I'm aware that they're offering training sessions, and I think they've even changed this into like a GIS integrated model. This is a model that is time tracking, so it's not just a single event, but it does track moisture through time. And it also not only includes significant processes, but it goes into processes in some detail. Okay, so let's start looking into the nuts and bolts of what a model like this does hydrologically. Here's the vertical water balance component. You can see that there are evaporative terms, of which there are 5, and that's because there's soil evaporation, which means that all the water that's intercepted from the canopy, and O is the overstory, and U is the understory. So E is evaporation, I is intercepted water, and then over or understory. ES, that's evaporation from the soil. There's also transpiration, so that's ET for the overstory and understory. So that's 5 different types of evapotranspiration. So you can see already, just compared to this, the SCS, rainfall runoff curve number approach that we did for lump modeling, we've got a lot more hydrology going on here. From a storage perspective, there's water stored all over the place. There's the overstory, storage, understory storage, and then soil stored in 2 different soil layers, which are shown here in light brown and dark brown. In addition, there are rooting zones that are there, and then other vertical fluxes. Okay, so I should just mention that in this case, runoff occurs as a saturation excess. So you have to fully saturate the soils before runoff can occur. That means that this model does not represent Hortonian overland flow. Okay, so in addition to that, there is a snow component and an energy model. What happens here is that you look at the air temperature. If the air temperature is below freezing, the assumption is the precipitation is falling as snow. Otherwise, it would be rain. There's a full energy balance, and all the terms in red here are energy balance. You've seen those before. If not, go back to podcasts like 2 or 3 or something, and you can review that. The energy balance is also used to calculate some snowmelt components, so snowfall. Some of the snow may sublimate, snow may be intercepted by trees, and then the snow can through fall. It can have either meltwater drip or just a mass release of snow. Penman-Monteith equation, remember that one? It's used to calculate the potential atmospheric water demand, and then intercepted water is evaporated away from, through time at that potential rate. So you can see there's just a lot of things that are going on here, a lot of different terms that, most of this is stuff you've seen. We've just never put it all together into a modeling framework like this. When we look at the spatial aspect of DHSVM, water can move from cell to cell as overland flow, subsurface flow, groundwater flow. There's upwelling and infiltration and reinfiltration. So that's like, transmission losses. So there's a lot of things that are taking place, but it's basically going to be moved according to those rules that govern, like a D infinity. I'm sorry, not D infinity, D8, path of maximum descent or something like that. Okay, so that's the innards of the hydrological modeling. And in addition to that, there's the whole GIS aspect of it. So you have to have topographic data, meteorological maps that are also time series to drive this whole thing. So that's a lot. You have to have land surface data, for example, soils map, and there's a source of soils map called StatsGo. That's the state level soils information. Then you have to process topographic data to delineate the watershed you're interested in, get the flow paths. You also have to look at the topography to look at what we call the aspect of the hillside, to say, as the sun goes across the sky in the morning, it's going to hit south-facing slopes, and east-facing slopes, but then in the afternoon, it's primarily going to hit south and west-facing slopes. So those are some of the examples. There may be other kinds of data you put in. You need to get channel networks, get all these layers in, and then finally all that goes into DHSVM, and it's going to produce your hydrological outputs, which is going to be, well, not only water storage components, flux components, but also energy storage and flux components as well. So let's look at a scientific question using this model. What are the hydrological impacts of forest clear cutting? I mean, that's obviously one of the big things that we've been looking at all quarter. But now we can go into much greater detail eco-hydrologically. So we're going to look at rain on snow events and radiation-dominated snowmelt, so 2 different events. We're going to look at it in a lot of detail in terms of spatial complexity. We're also going to look at the effects of selective versus complete forest harvesting on runoff. And then finally, we'll look at the impact of road networks on stream flow. One of the key variables that is going to be used in this is called snow water equivalent. So I don't think we've seen that before, but it has the letters SWE as an acronym, and it's just the amount of water within the snowpack. So if you took a huge chunk of snow, if you took all the snow in the watershed and you melted it all, that total amount of water would be the SWE. Now, a lot of the graphs I'm going to show you are very new to you in that they convey a lot of information using colors and color ramps. If you're red-green colorblind, then I apologize because science is not serving you very well. For example, here, there's a lot of red and green. So if you have more questions about that, let me know. So depending on which plot you look at, the interpretation of what the color scale means is different. For example, for all the plots that are for the year of stand origin, the color goes from purple to red, which is the year of 1780 to 1995. If you're looking at an elevation plot, it goes from 400 to 1800. If you're looking at vegetation type, then it's the colors go with those names of vegetation that are given. So there's 3 different watersheds here. There's this North Fork Snoqualmie, there's a Little Natchez, and then there's Hard and Ware Creeks. For those, there's a DEM in each case, there's the vegetation type, and then that history. So these red areas are areas that were probably clear cut and then have a relatively young stand, whereas the areas that are shown like in these blues and purples are long established forests. So let's look at the first case of North Fork Snoqualmie, and there was a rain on snow storm event after logging. And you can see December 3rd, 1989, December 4th, 1989, so that's 2 days. The first thing is, of course, we got the DEM over to the right, but I think that's pretty self-explanatory. So the first plot in the upper left shows the snow water equivalent going from 0 millimeters to 1,000 millimeters on December 3rd in the clear-cut case. So in the clear-cut case, what you can see is that there initially is snow, unless it's white, right? But all these like violets to purples to green, there's less snow in the lowlands and more snow in the uplands. If you compare the same starting state with the vegetated run, because remember we're running the same model, the same system, just with and without vegetation, you can see that there isn't a significant difference between the two. There's a little bit more snow in the lowlands than there was without the clear cut. Now, as after the rain on snow event, you can see that the low elevation valley area here has been completely lost all of its snow. It's just the snow has melted away. Whereas for the vegetated case, there's still snow. Now this raises an important point for ecohydrology. Does vegetation protect snow, or does vegetation cause snow to be lost? The first insight you might have is that when there's snow on the ground and you have vegetation above it, that the vegetation is going to provide shading, and that shading will therefore reduce the energy impacting the snow and cause the snow to remain. However, it's more complicated than that. First of all, the trees themselves are sources of heat, and so you often will see a ring of dry soil around the base of a tree, or at least less snow because of that. Another thing is that trees intercept snow. Just think about it. I know if you go up in a forest, if you ever go skiing or anything, and you look at the trees, they're just chock full of snow. And in fact, on the interception video podcast, I showed a photo. If you want to go back, you can see a tree just totally like buried in snow. And most of the snow that's intercepted by a tree is going to evaporate away. But that's also a key question. How much of that? Like, will there be a lot of melt of that, or will it evaporate? It could evaporate, it could sublimate. So that's a key thing, is like, if you have too many trees, it's all going to get caught up in the trees and the snow will evaporate and there'll be less snowpack available. If the snow can get on the ground, then you might have some shading effects. Now, of course, when you're looking at a complicated distributed hydrological model, you just don't know what's going on the inside. But in this case, the implication is that there is retention of snow in the lowlands, and as a result of that, and you can see the significant difference in the amount of snow, especially up in these tributary valleys. White means a complete loss of snow, and then here you still have violets and purples. So the trees in this model are, as a net effect, shading and protecting the snowpack. The bottom thing here shows the snowmelt difference during the day, and it shows that the difference between these two snow water equivalents. To just highlight, so you can see that the main difference in terms of snowmelt, and we're going from -1 being snow accumulation, white means snowmelt, and then red means snowmelt of 3 millimeters per hour. So you can see that over the course of the day, the snow began to melt in the valley, and then the melt extended up through the network. So in a way, it's almost like the variable source area concept all over again. That starting from the lowest elevations and working outward and upward, you get increasing amounts of snow melt. It makes sense that that would follow a VSA approach. Now let's look at another scenario. This is radiation-driven spring snowmelt after logging. The first row is the clear-cut scenario, the second row is the vegetated scenario, and then the third row is the difference between the two. So you can either see the difference by just visually comparing the colors, or going to the third map, and then the colors there represent the difference. The top is the rate of snowmelt, so for the top 6 maps, snowmelt goes from 0 to 9 millimeters per hour. For the bottom three maps, the snowmelt difference goes from -7 to +9 millimeters per hour. What you can see is that we're going on a one day at 9 a.m. to noon to 3 p.m. And where the white is, that is the bottom. So imagine a V-shaped valley. Where the white is, I'll try to draw it, let's say like that. Okay, where the white is, that's the bottom of the valley. Now, if you imagine a slope, if the sun is moving across the sky, like my finger here, here's the sun, okay, it's going to be shooting its energy, so to speak, on that face. On the other hand, if you have the other side of the valley, the sun's coming across, the sun's shooting, it's not going to be on that face. So, take your fingers, make a V, push the sun across the sky, and you'll see that as the day goes on, one side is getting hit, then the sun's across the sky, and then the other side gets hit. And that's what you see here. These yellow and green colors, if you imagine that the bottom of the valley is white, of course, the yellow and green colors for all three of these fingers of the valley are all on the east-facing side. The east-facing side, it's getting hot, and that radiation, not just heat, but just direct sunlight, is melting the snow. By midday, it's already preferentially on the west side, and then in the afternoon, the total rate is lower, but it's still preferentially on the right. I know that because green is more snowmelt than blue. So if we look at this middle one again, the east-facing hill has relatively low. It's higher, of course, but it's still relatively low compared to the west-facing one. And in the morning, it was the highest. Now look at the vegetated scenario. You don't see any of that effect. In the vegetated case, the snowmelt is most occurring, let's see, in the lowlands, and then more so, less in the tributaries, and then least at the hill crests. Later in the day, it's still primarily centered in these low areas. So the presence of vegetation does substantially block radiation-driven spring snowmelt. On the other hand, for a rain-on-snow event, you don't see that effect so much. You pretty much see more of a variable source area-driven melting, but vegetation is still playing a fact. It just isn't creating that east-to-west phenomenon the same way. Okay, now we're going to move to the next question that we had, which was looking at different amounts of logging. Here's a digital elevation model for this Little Natchez River. Here is the distribution of the overstory. So overstore planting from 1700 to 1995. If it's red, it essentially means that it's freshly been logged. And if it's blue or purple, it's pretty long-lived. So this is the current condition. We could compare that to the maximum potential harvest that's shown here. Okay, and then what you see here is for two different months, May and April. These are the snowmelt months. There's the amount of the increase in snowmelt as a result of having the maximum potential harvest compared to the current condition. So if we are yellow to red, we're getting more snowmelt than if we did not log. And you can see the majority of the watershed is in yellow and orange kind of condition. So in May 1993, they had some data. The main effect is in the upland areas. And then for the next one, it's pretty ubiquitous because these are just different months with different scenarios. But overall, it is showing that the effect of harvesting the forest on a watershed is to increase snowmelt. This is another way of looking at it. This is for the North Fork of the Snoqualmie. If we look at the annual net streamflow change for complete logging, you'll see that this is through time from October 1989 to January 1991, and the streamflow is either less than typical or, compared to the baseline case without logging, like the current condition, that would be 0. So you either have an increase in streamflow as a result of logging or a decrease. And what you can see that it's not that deforestation is uniformly increasing snowmelt and streamflow. It's that during the periods when there's lots of snow, which is during the winter and especially in the early spring, that you get a lot more streamflow associated with that snowmelt. But once the snow is gone, then now you have an absence. And so compared to the base case, like the current condition, which has a forest, the forest protects the snowpack so that it allows snow melt to be slower and have a longer duration into the summer. Without that vegetation, all the snow melts very quickly, and you end up in a deficit of water by the time you get to the early summer. Okay, the last thing, this example for a distributed hydrological model is looking at the hydrological impacts of roads. So here's a schematic of a road. The road is shown over here as this flat surface. Towards the hillside, you have like a hillside, and the hillside would just go straight down. You're putting a flat road in there, and so that creates a slope break. So the way that's done is they have to cut dirt out of the hillside to make space for the road, and then put the fill in on the downward side. And then associated with that cut, there's usually a channel that's like a roadside ditch. So when you cut into the slope, there's going to be a water table location that you will be intersecting. It may not be there during the dry condition when the road is built, but when it's wet and you're in a mountain context, then you will have that. And that's another thing, is when we're talking about impacts of roads, I do mean in a mountainous watershed context where the topic of logging and road effects is important, not on the bottom of the Sacramento Valley floor. Okay, so anyway, so on a relatively steep hill slope, you're going to intersect the water table, and that means that the water that would otherwise be flowing in the subsurface is now going to seep out and, of course, go into that ditch. So the question is that with those sorts of effects, what are the consequences? In addition, when you build a road that's going along the side of a mountain, it's also going to be blocking streams. So you might have a stream that would otherwise be flowing, and so then you have to put in a culvert for that water to go. That means that the road ditch that's intercepting the hill slope water is going to have to be deferred into those streams. It could be deferred into a culvert, but then just have the water try to infiltrate, like an infiltration strip or something. It could be that you want it to infiltrate, but instead it creates a gully, like it just trenches down because you have that concentrated water instead of having a diffuse subsurface flow. And it might be that there's this case D, you have a gully, but the gully does then, so you have a gully, in this case, the gully erodes and connects all the way to a stream versus a gully that's just in an early, incipient phase of just starting. So if we compare the DHSVM model results for the two different creeks, either using the roads or not using the roads, the no roads is solid line, roads is dashed line, you can see that the effect of roads is to substantially increase the peak. There's a slight decrease in the time to peak, and there's an increased rate of the recession of the flow on the falling limb of the curve of the hydrograph. Okay, so that summarizes the DHSVM. We looked at like 3 broad examples. We saw that, if we go back to the questions, the effect of logging on rain on snow and radiation-dominated snowmelts, it's significant. Like if you log, then radiation is going to have a much stronger effect on it. There is one thing that isn't being accounted for, and that is that trees also put debris onto the ground. That debris can help to increase the albedo, which means that there'll be more. It'll make this, basically it makes the snow darker. So it's actually the other way. It makes the snow darker, and by making it darker, more of the sun's energy will be absorbed into the snow and create snowmelt. So there's really 3 effects of trees. There's 4. There's the heating effect of the tree, there's the interception effect of the tree, there's the debris effect, and then there's the shading. And they're all competitive, and so only, the one that wins, according to this model, is the shading effect. However, I have seen for other forests and other 2D model other spatially distributed hydrological models, that you get the other case, that the interception effect wins, and that the effect of forests is actually to promote snowmelt loss. And in fact, by logging the forest, you would promote snow retention and a longer snowpack. So the way different distributed hydrological models represents forests and their eco-hydrological effects is crucial because that's going to determine what kind of management should be done. Okay, moving on, just a few other things. There's a lot more you can do with distributed hydrological modeling than just look at those runoff processes. For example, one thing we can do in a mountain context is look at the risk of landsliding. Now, landsliding occurs when you have an oversaturation of the soil, given the fact that you have very steeply sloped soils, relatively shallow bedrock, and so the soil has a tendency, it's going to want to slide, right? I mean, you've got the force of gravity driving it down. It's resisted by both the internal friction in the soil and the shear at the interface between the soil and the bedrock. Well, when you lubricate that soil with water during a rainstorm, then you substantially decrease the resistance to landslide. And there are equations that can predict that, and I go through that in my hill slope geomorphology and sediment budgets class. But what this shows here is a map where critical rainfall is how much water do you need before that hill slope would fail. If it's red, it means that even in a dry condition, it's already unstable. Like the slope is so steep that the soil probably isn't going to survive there. And then as you go through these different shades of yellows to blues to green, green means that no matter what, it doesn't matter how much rain you have, it's unconditionally stable. And usually that's because it's relatively flat. So you can see here that there are these very steep slopes on the side slopes of this hill, and a mountain, and they're quite unstable. And then around that, there are areas that are, given enough rain, they would trigger. And then the last example I'll just show very quickly is that for a flatter landscape, you could look at the risk of soil erosion. And this shows a distributed hydrological model that also includes a sediment transport component. And so it can track through time, cut on the land, and then fill in the channel. So the darker the red, the more the land is eroding, and then the bluer these channel areas are, the more fill they're receiving. So obviously that's beyond the scope of the class, but it's something that is possible. Okay, so that gives you a sense of some applications for distributed hydrological modeling, and I think you can see how valued that would be. We don't have time to actually run a distributed hydrological model in this class, but if you're interested in that, then you've got the basic tools to move forward with that.